Video is a little bit different because voice uses a code, a way to transform the voice into binary value, which is called a codec, that is very consistent. So if you use a given codec, it's going to generate a certain packet size at a certain speed, maybe 50 packets per second, each of them being 116 bytes, for example. So that's a very consistent flow from the phone side into the stack. And then the stack's job is to empty that into the air, as we saw. Video is different because you have three types of video frames. Some of them are the initial frames. And imagine that video tries to save on bandwidth because we understand that video is very bandwidth intensive. Imagine that you have to depict a landscape with a car driving somewhere in the background. So you will have that frame that draws the entire landscape with the tree, the sky, etc. And that is of course going to be depicting every single pixel of the image. And that's very bandwidth intensive. But then if there is only one car moving somewhere in the background, what most codecs are going to try to do is to try to only describe the variation of that frame compared to the previous frame. So that differential frame will have different name, B and N, depending on how it's built, but it's going to only describe the variation. So that's going to drop the bandwidth consumption a lot because you're just describing a tiny difference in one area of the frame. Then at regular intervals or whenever you change the view, you will have to redraw the entire frame again, and that's going to be very bandwidth intensive. So you see video is much more bandwidth intensive than voice, but also the bandwidth consumption changes over time depending on what kind of display you're depicting in this image. So that makes video very different from voice. But there are in fact three types of real-time videos. What we call the interactive real-time video, and that's video conference, for example, where typically you may have some bandwidth consumption, but most of the time people are more interested in hearing what is being said very clearly than seeing a nice picture of your face. So for that interactive type of video, if you have some issues in the bandwidth for video, it's usually not a big problem. Then there is what we call the streaming video. And streaming video is typically when it's a one-way communication and you receive some flow from another side. If this is real time, this is not YouTube or this is not Netflix. This is a real feed where you see something live, for example, like a live TV show. So for that, typically, you watch the video as well as you listen to what is being said. So you also want the video to be of good quality. And that two conditions bring us to this categorization between elastic and inelastic video. Elastic video is that kind of video that dynamically can detect the bandwidth between the receiver and the sender and adapt the codec, the bandwidth consumption, dynamically to those network conditions. So those can suffer from losses or changes in conditions because they will adapt dynamically. But there is also some inelastic video, and that type does not adapt to the changing conditions. So the way you design for real-time video will be depending on if you design for interactive, if you design for streaming, and if you design for a codec that is elastic or inelastic. So what does that mean? That means that when you design for real-time applications, you first have to know what real-time application you're designing for, and you have to measure how much bandwidth that application is going to use. So first do that. Measure the bandwidth of that target application. Do not just design generically. Once you know the bandwidth you're going to consume on that application, well, you just multiply by the number of users that you expect to be using that application at the same time. It's not number of users in the cell, right? It's the number of users using that application at the same time. And when you do that multiplication, that gives you the bandwidth you need in your cell. And as you know, you're slower at the edge of the cell, so that means that this is the application speed and the cell speed that you need at the edge of your cell. Okay, let's take an example. Suppose you have a medical center and they tell you, we need to design for multiple things. First, we will have some video calls, and in any given cell, we expect that at least 2 people at any given time may be talking. At the same time, in the same cell, we may have up to 5 audio calls. And we may have some other users, up to 12 per cell, actively using the network just to browse. So how much bandwidth do you need? Well, just do the math. If you calculate how much bandwidth your Skype call is using, you can find that, for example, a video call on Skype consumes 1.2 megabit per second. Times 2 because it's a two-way communications, and there are 2 communications at the same time, you have 4.8 megabit per second. Then 5 audio calls, same thing, you measure, and you find, for example, that you need 600 kilobit per second on top of the 4.8 mega. And then you have 5 other people that may be browsing, and you give them, I don't know, maybe 250 kilobit per second, which is a lot. Then you find that you need 6.65 megabit per second at any given time in your cell. And that is, of course, at the edge of the cell, where the network is slowest.